Hello, let's start this video with a simple question. What exactly is a computing system? Today, even elementary school students can tell you it's all about the input processing output cycle. A typical setup includes input devices like keyboards, touchpads, mice, or microphones, processing units such as the CPU or GPU, and output components like speakers, monitors, and printers. It's become such common knowledge that we barely think twice about it. But here's the thing, computers weren't always this way. The architecture we rely on today owes a lot to the groundbreaking vision of John von Neumann. Without his contributions, computing as we know it would have been far more complex, and who knows, AI might not even exist now. Artificial intelligence is often seen as a product of recent technological revolutions, but its intellectual roots stretch deep into the 20th century. Among the constellation of thinkers who paved the way for intelligent machines, few loom as large as John von Neumann. A polymath of rare genius, von Neumann made lasting contributions to mathematics, physics, economics, and computing. While he never designed an AI system per se, the foundational work he did across multiple domains now serves as the intellectual scaffolding for much of modern AI. At the heart of his legacy lies the von Neumann architecture, a conceptual model for digital computers that, while not AI itself, forms the substrate on which nearly all contemporary AI operates. Proposed in 1945 in a seminal report titled First Draft of a Report on the EDVAC, the von Neumann architecture revolutionized how machines were conceived. At its core, this model proposed a computer structure based on three key components: a central processing unit, CPU, a memory unit, and input-output mechanisms. Crucially, it introduced the concept of storing both data and program instructions in the same memory space, enabling machines to be reprogrammable. Before that, engineers had to physically reconfigure circuits, manually rewiring cables, flipping switches, and rearranging panels. It was labor-intensive, time-consuming, and highly inflexible. This architecture is not inherently intelligent. However, it provides the essential environment within which intelligent algorithms can operate. Every AI system today, from simple rule-based chatbots to complex neural networks, runs on hardware that follows von Neumann's input-process-output (IPO) framework. In this sense, von Neumann didn't just help build the first computers, he laid down the blueprint for how machines would process and act upon information, a cornerstone concept in AI. The idea of a stored program computer made it possible to implement flexible, learning-based algorithms. Without this architectural innovation, the development of adaptive software systems, which define AI, would have been severely hampered. Von Neumann was not content with just building machines. He was deeply intrigued by how the brain itself functioned as an information processor. This fascination culminated in his posthumously published work, The Computer and the Brain, 1958. In this book, he drew a comparison between the digital computer and the human brain, highlighting both their similarities and their crucial differences. He noted that while digital computers operated sequentially with precise binary states, the brain functioned in a massively parallel and probabilistic fashion. The brain was fault-tolerant and analog, whereas computers were brittle and digital. Still, he believed that understanding one could illuminate the other. Importantly, this perspective helped shape the foundational view in AI known as computationalism, the idea that cognitive processes are a form of computation. By framing the brain as a machine, von Neumann helped validate the pursuit of artificial systems that could replicate human-like thinking process. Von Neumann's work in game theory, particularly through his collaboration with economist Oscar Morgenstern in Theory of Games and Economic Behavior, 1944, introduced rigorous mathematical frameworks for decision-making in competitive environments. Concepts such as zero-sum games, utility maximization, and equilibrium strategies became crucial tools not only in economics, but also in artificial intelligence. In game theory, a zero-sum game is a situation where one player's gain is exactly balanced by another's loss, meaning the total payoff across all players remains constant, typically zero. This creates a purely competitive environment, where the success of one party directly comes at the expense of another. Within this framework, players engage in utility maximization, making decisions that maximize their own expected utility, which reflects their preferences or payoff. The assumption is that each player acts rationally to achieve the best possible outcome for themselves. A key concept that emerges from this is that of equilibrium strategies, where each player's strategy is optimal given the strategies of others, so no one has anything to gain by changing their strategy unilaterally. Together, these concepts provide a powerful mathematical foundation for analyzing strategic decision-making in economics, AI, and beyond. In artificial intelligence, especially in fields like multi-agent systems and reinforcement learning, agents must make decisions that maximize their expected utility, often in environments shared with other agents or players. Game theory provides the language and structure to formalize these interactions. Von Neumann's minimax theorem, for example, is directly applicable to adversarial games and has influenced the design of algorithms used in AI systems like IBM's Deep Blue and DeepMind's AlphaGo. It provides a basis for algorithms where an agent seeks to minimize its maximum possible loss or maximize its minimum gain against a rational opponent. Moreover, modern developments in AI safety, alignment, and goal modeling often draw upon game theoretic ideas. Understanding how agents might strategize in environments with incomplete information and competing objectives is foundational to creating robust, general AI. One of von Neumann's most visionary contributions was his work on cellular automata and self-replicating machines. In an attempt to model how biological systems might replicate themselves, he devised a mathematical structure where simple units, cells, followed basic rules, but could generate highly complex behaviors over time. In John von Neumann's original cellular automaton model, he designed a system with 29 different states per cell. In modern AI, techniques such as genetic algorithms and other bio-inspired methods owe much to the conceptual groundwork von Neumann laid. These approaches leverage emergent behavior, the idea that simple rules at the micro level can produce intelligent behavior at the macro level. Von Neumann's cellular automaton model was a precursor to emergent computation. In emergent computing, intelligence doesn't need to be hard-coded. Instead, it can emerge from interactions among simple elements, especially in learning systems. The notion that intelligence could arise from simple units following simple rules remains a foundational idea in fields ranging from neural networks to agent-based modeling. In agent-based systems, many simple agents follow straightforward rules, and researchers study how their collective behavior leads to large-scale patterns. This is directly in line with the spirit of cellular automata. Von Neumann, along with colleagues like Stanislaw Ulam and Nicholas Metropolis, was instrumental in the development and application of the Monte Carlo method, a statistical technique that uses random sampling to estimate numerical solutions to complex problems. This method, originally applied to nuclear physics problems, has become a staple in modern data science and AI. The Monte Carlo method was significantly advanced during their work at Los Alamos, particularly for tackling complex problems in nuclear physics related to neutron diffusion for the Manhattan Project. Von Neumann played a key role in adapting these methods for use on early electronic computers like ENIAC and MANIAC. In machine learning, Monte Carlo methods are used in probabilistic reasoning, Bayesian networks, and reinforcement learning. Techniques such as Markov chain, Monte Carlo, MCMC, are essential for training models that must navigate uncertain or high-dimensional spaces. His embrace of simulation as a valid form of scientific experimentation also influenced how AI researchers build and test intelligent agents. Simulated environments allow for rapid iteration and safe testing, from training robots in virtual worlds to fine-tuning recommendation algorithms before real-world deployment. Beyond his technical contributions, von Neumann also offered profound philosophical insights. He grappled with the implications of machines that could think, learn, and perhaps even replicate themselves. Von Neumann was certainly aware of the profound differences between the digital computers he helped design and the biological brain. He recognized the challenges in modeling the brain's complexity, parallelism, and potentially non-digital aspects, which implicitly touches upon the difficulty of modeling consciousness purely through the computational paradigms known at the time. In this influential, albeit unfinished, work, von Neumann explicitly contrasted the serial, digital, high-precision nature of computers with the massively parallel, lower-precision, statistically operating nature of the brain, which likely involves both analog and digital signaling. By highlighting these differences, he indeed raised fundamental questions about whether a system operating on purely digital principles, as understood then, could fully capture the essence of the brain's function. The term fuzzy aptly contrasts the brain's apparent operational style with the crisp logic of digital machines. The questions von Neumann grappled with remain remarkably pertinent. Discussions surrounding artificial general intelligence, AGI, machines with human-like cognitive abilities, the nature of consciousness, and whether it can emerge in non-biological systems, and the ethical implications of creating potentially autonomous and self-replicating intelligent machines directly echo the foundational issues von Neumann explored decades ago. Although von Neumann did not live to see the explosion of AI research, his intellectual fingerprints are everywhere. The very hardware that runs AI systems is built in his input-process-output architecture. The theoretical frameworks that guide decision-making, learning, and adaptation owe much to his theory of digital mind and game theory. The speculative vision of machines that learn, replicate, and evolve springs from his pioneering work in automata theory. His Monte Carlo method also laid the foundation for subsequent machine learning algorithms. In this sense, we are all still working in the house that John built. In a world increasingly shaped by intelligent machines, the relevance of von Neumann's work only continues to grow. His vision reminds us that the quest to understand and replicate intelligence is not only a scientific endeavor, but also a profoundly philosophical one. So, what do you think? Drop your thoughts in the comments. I'd love to hear your feedback. If you found this video helpful, please give it a like, share it with your friends, and don't forget to subscribe to the channel for more content like this. Thanks for watching and see you in the next one.